The world just spent $3 trillion on solar panels and wind turbines, and we still haven't solved the most fundamental problem in the history of energy. The sun goes down at roughly 6 in the evening. In most cities, that is exactly when energy demand peaks. Factories still running, millions of people returning home, switching on lights, air conditioning, appliances simultaneously. Electrical engineers call it the duck curve. That collapse in renewable supply at the precise moment demand peaks is not a minor inconvenience. It is the central engineering problem of the clean energy transition. The current answer is lithium-ion batteries. Store energy when the sun shines, release it when the sun doesn't. But lithium has problems that become more serious the larger the scale. The costs are enormous, the materials come from politically fragile supply chains, and a lithium facility storing grid-scale energy is, at its core, a warehouse full of highly combustible material. What if the solution has nothing to do with chemistry? What if the answer is something more primitive, more durable, more simple than any battery ever built? What if the answer is gravity? The lithium illusion and pumped hydro. Lithium-ion technology is extraordinary at the consumer scale. But when you scale it to the level a modern electrical grid requires, hundreds of megawatt hours of capacity, a different set of problems emerge. The cells degrade. Every charge cycle diminishes capacity, meaning a multi-$100 million grid installation is a depreciating asset from day one. Thermal management systems required to prevent runaway heating are expensive and complex. And the levelized cost of storage, the true metric for comparing storage technologies over their operational lifetime, remains stubbornly high when all costs are accounted for. There is an alternative that actually works at grid scale. Pumped hydro storage has been operating for decades. Use surplus electricity to pump water uphill into a reservoir, then release the water through turbines when the grid needs power. Efficient, proven, reliable. And it accounts for the vast majority of grid-scale energy storage on Earth. The problem is geography. Pumped hydro requires significant elevation change and large volumes of water. Sites that meet both criteria have largely already been developed. But what if you didn't need the mountain? What if you could build one instead? The $600 million startup Energy Vault. Energy Vault was founded in 2018 in Lugano, Switzerland, by CEO Robert Picconi and Chief Technology Officer Andrea Pedretti. The concept is almost aggressively simple. Instead of pumping water uphill, you lift weight. Specifically, you use excess renewable electricity to power automated cranes that lift 30-ton composite blocks made from coal mine tailings, fiber, and soil waste hundreds of feet into the air. You store the energy as gravitational potential. When the grid needs power, you lower the blocks in a controlled descent, driving a generator. Pure kinetic energy. No chemicals, no combustion, no thermal management. The blocks themselves are an engineering decision worth examining. Energy Vault does not use conventional concrete, which would require enormous quantities of mined material. Their composite blocks are manufactured partly from waste material, coal fly ash, excavated soil, recycled composite fiber, meaning the company can source its storage medium from the local industrial waste stream, rather than a global supply chain. The embedded carbon footprint of the storage medium is, in principle, substantially lower than lithium cell manufacturing. The company's EVX system, their current commercial product, is a purpose-built tower structure housing multiple cranes operating simultaneously in a coordinated choreography managed by proprietary software. The automation layer is significant. There are no human operators moving individual blocks. The system monitors grid demand in real time, decides which blocks to raise and which to lower, and adjusts continuously based on the energy signal it receives from the grid. Energy Vault went public through a SPAC merger in 2022 at a valuation of approximately $1.7 billion. The company has secured over $600 million in project commitments globally, including partnerships with Atlas Renewable Energy, Saudi Aramco Energy Ventures, and China Tianying, one of China's largest waste management and infrastructure conglomerates. Their first commercial scale deployment is operating in Rudong, in China's Jiangsu province, a 100 megawatt-hour facility that went live in 2023 and represents the largest gravity-based energy storage installation on Earth. The economics, why Wall Street cares. The metric that matters most when evaluating any energy storage technology, levelized cost of storage, LCOS. This is the total cost of deploying and operating a storage system, divided by the total amount of energy it delivers over its full operational lifetime. It accounts for capital costs, maintenance, degradation, and the efficiency losses inherent in the storage and retrieval process. Lithium-ion grid storage is currently running at somewhere between $150 and $200 per megawatt hour when you factor in degradation replacement costs over a 10 to 15-year commercial lifespan. Pumped hydro, where geography allows, can achieve costs below $100 per megawatt hour, but with upfront capital requirements that make it inaccessible for most deployment scenarios. Energy Vault's published LCOS projections for their EVX system target a range below $100 per megawatt hour over a 35-year operational lifespan, a number that, if achieved at commercial scale, would represent a significant competitive advantage over lithium. The case for that projection rests on three claims: no chemical degradation over time, lower maintenance costs than lithium thermal management systems, and a storage medium that does not depend on a global commodity supply chain subject to price volatility. The Rudong deployment is the stress test. It is the largest real-world dataset Energy Vault has ever had access to, and the performance data coming out of that facility will determine whether the Wall Street interest reflected in the company's project pipeline converts to actual long-term capital commitment. The critics. Is it a scam? Energy Vault has its skeptics, and several of the criticisms are technically substantive. The first concern is round-trip efficiency. The process of converting electrical energy to gravitational potential and back to electrical energy involves losses at every stage. Energy Vault claims round-trip efficiency of approximately 80 to 90%. Independent engineers have questioned whether that figure holds under real operating conditions across all weather scenarios. For comparison, lithium-ion typically achieves 85 to 95% round-trip efficiency, and that gap in efficiency compounds meaningfully at grid scale over years of operation. The second concern is wind loading on the EVX tower structures. Moving 30-ton blocks at elevation requires cable systems and crane mechanisms operating in ambient wind conditions. Critics have raised questions about the durability and maintenance requirements of those cable systems under sustained outdoor operation, particularly in coastal or high wind environments. The third concern is geographic concentration risk. Rudong, China represents the overwhelming majority of Energy Vault's operational track record. A single facility in a single regulatory environment is not a proof of concept at global scale. Skeptics argue that the company's LCOS projections may not translate across different labor markets, material costs, and grid configurations. None of these criticisms are necessarily fatal, but they are real, and the burden of proof for a company claiming it can outperform lithium on price while using 35-year-old crane technology built from industrial waste is appropriately high. Gravity-based energy storage is not science fiction. A 100 megawatt-hour facility is operating right now in Rudong, managing real grid demand using physics that Newton described in 1687. What is still being determined is whether this approach can scale to the level the transition to renewable energy actually requires. Whether the engineering holds across geography and climate, whether the economics survive contact with real construction costs in Western markets, and whether a company that went public via SPAC at the height of clean energy enthusiasm can maintain investor confidence through a more demanding capital environment. What is not in question is the logic of the underlying physics. Gravity does not degrade. Concrete does not combust. A block lifted into the air will fall when released, and the energy released in that fall is real, measurable, and extractable. If the execution catches up to the elegance of the concept, We will look back at the decision to build trillion-dollar grid storage from lithium chemistry as the obvious, avoidable mistake it may turn out to be. This is the kind of breakthrough infrastructure we cover here at Apex Engineering. If you want to understand the megaprojects shaping our future, subscribe. See you in the next video.